In this video, we are going to go over some practice problems for the final exam. So let's get started here. So in the first problem, we have to construct a solution for the max clique problem using a black box that can solve vertex cover problem. So recall the max clique precision problem is as follows. So the input is a graph G and a positive integer k, and the question we ask is, does G have a clique of size k? So recall that if you in a graph, a clique of size k means there is a subset of vertices or which has k vertices such that every vertex has an edge, every pair of vertex has an edge between them. So for example, a clique of size 4 would look like this. So every pair of vertex in this clique will have an edge between them. So that's a clique. Now the definition for so recall that the vertex cover problem looks like our input is a graph G and again a positive integer k, and the question is, does G have a vertex cover of size k or at most k, right? So recall that vertex cover is a subset of the set of vertices such that um, every edge in the graph has at least one endpoint in this vertex cover. So for instance, let's say this is a graph. Let's say this is a b c d and e, right? So if we want to pick a subset of vertices such that every edge should have at least one endpoint in that subset, right? So for example, here if we pick, let's say, b and d. So if you pick b and d, ab has one endpoint which is b, cb has one endpoint b, is in d we have cd has one endpoint and ed has one endpoint, right? So every edge has one endpoint. So b comma d is one vertex cover here. So the question is saying, assuming that we have an efficient algorithm for solving the vertex cover problem, how would we efficiently solve the max clique problem? Okay, so recall in class when we did this, we reduced the max clique problem to the independent set problem, and then we reduced the independent set problem to the vertex cover problem. Now in this case here, we have to do this directly from vertex cover to from max clique to vertex cover. We saw in the class that if we are given an input graph that has a clique of size k, so let's say this is our graph that has a clique of size 4, right? Now let's say this is our input graph. We transform it such that uh, every pair of vertex that has an edge between them, we remove the edge, and every pair of vertex that doesn't have any edge between them, we add an edge, right? So if we transform this in this graph in this fashion, so let's say we get this g prime. Now here in this case, because this is a max clique, the every pair of vertex has an edge between them, and therefore if we do the transformation, if we remove the existing edges and add the edges that were not present in the graph, we simply get these four vertices in this case, right? So in this case, notice that this transformation with this transformation, the input graph G had a clique of size 4. Now this transform graph has an independent set of size 4. So we used this property to reduce the max clique problem to the independent set problem, right? And then you would further recall, to solve the independent set using vertex cover, we made use of this observation. So if you have an input graph G, and let's say you divide the set of vertices, so let's say this is vertex v comma e, set of vertices. If you divide it into two sets, the set of vertices, such that on one end you have just the independent set, so let's say this is your independent set S, and this is all the remaining vertices, right? So if you do this division, you'll find that the only edges that exist in this graph would be either between the between the pairs that are in this set v minus s, or they would be from this v minus s to the edges, sorry, to the vertices in S, right? There cannot be any edges between any two vertices within S, because this S is basically in an independent set, right? So basically what that means is, if we simply pick all the vertices here in this set v minus s, we will get a vertex cover by definition of vertex cover. And we also saw a theorem in the class which towards this end. So we saw that if v minus s, if this is a vertex cover, it implies that S must be an independent set, and if S is an independent set, it implies that v minus s must be a vertex cover. So to solve this problem, we would need to use all of these properties in this case. So if you have an input graph G, V comma E, and you want to figure out whether there is a max clique of size K, so we want to find out whether there is a max clique of size K, we first transform this graph. So we transform this graph just as we did this to get G prime, right? So we transform this into G prime V comma E such that if there was an edge between any two pair of vertices in original graph G, then we remove the edge, and if there was no edge between any two given pairs of vertices in G, then we added an edge in G prime. Okay, now in this transformed graph G prime, if the original vertex, if the original graph G had a max clique of size K, then this new graph G prime should have an independent set of size K. Okay, now let's find out whether it has, this G prime has an independent set of size K or not, right? So in class, what we did to reduce this independent set problem to vertex cover was we fed this graph G prime into this vertex cover black box. So let's say this is our vertex cover black box that can solve the vertex cover problem. So if you feed in a graph, this graph G prime, and here if you ask whether this graph has a vertex cover of size K, it will simply say yes or no depending on whether such a vertex cover exists or not, right? So if we want to find out whether G prime has an independent set of size K, we should ask this black box whether G prime has a vertex cover of size mod V minus uh, mod V minus K. If this vertex cover black box says yes, there is a vertex cover of size mod V minus K in this G prime, it means that this G prime has an independent set of size K, right? Which in turn implies that the original graph G had a max clique of size K. However, if this says no, it means G prime doesn't have an independent set of size K, which means the original graph G did not have a max clique of size K. Okay, so this is how we solve the max clique problem using the vertex cover problem. The solution is also summarized over here on this slide. So the two partition problem is introduced over here. The problem is you are given an input set of n integers. Let's say this is a set A which has a1 all the way up to an integers, and the problem is to partition this input set of integers into two subsets a1 and a2 such that the sum of all the elements in a1 should be equal to the sum of all the elements in a2, and basically these sums should be half the sum of all the elements in the original set. Okay, so we basically have to partition this original input set into two subsets of equal weight, and the additional constraint here is that each element in A should appear in exactly one of the two subsets. No repetitions are allowed and no element can be left out. So this is the search version. The decision version of the problem is as follows. The decision version says that you are given a set of n integers A, and the question is, can we partition A into two groups such that the sum of the elements in both the groups is equal? Okay, so the first question here is show that this two partition decision problem is in NP. So recall, to show this we have to basically show three things, right? So first is whether this is a decision problem. Second, what if for yes inputs, what proof would prover provide to the verifier, and the third thing is how would verifier verify the provided answer in polynomial time is correct. Okay, so here is the solution to the two partition problem, whether it is in NP or not. The first thing we say is that this problem is a decision problem. That's because the output is a binary output. It's a yes or no question whether it is possible to partition the input set into two subsets that add up to equal weights. For a yes input, the prover can simply provide the two groups A1 and A2, the two subsets A1 and A2 that have equal sums. So for example, if your input set was A, let's say it was 2, 3, 5, right? So it is clearly possible to divide this A into two subsets A1 that add up to 5, right? A1 and A2. So your A1 would be 2 comma 3 and A2 would be simply 5 in this case, right? So the prover can simply provide this these two subsets A1 and A2, and the verifier will basically have to first of all check what is the addition of all the elements in A. So in this case, for example, that is 10. This 2 plus 3 plus 5 is 10, and then it will compute 10 by 2, which is 5. Now it will check whether A1 adds up to 5 and A2 adds up to 5. In this case, it should further check that every element that appeared in A, it must appear in exactly one of A1 and A2, right? So no repetitions and no element can be left out, right? So that is also true in this case. So that this all of this verification can be done in polynomial time. So adding all the elements of A can be done in O of n. Adding all the elements of A1 and A2, again O of n operations each. Verifying that each element appears only once in either A1 or A2 and none of the elements are left out. This also can be done in O of n. Okay, so basically the verifier can verify in polynomial time that the provided solution is correct, and therefore this problem is in class NP. Recall that the subset sum W problem is as follows, right? So you are given a set of integers, and the question is whether there is a subset of this set that adds up to some constant W. Okay, so for example, if your input set is, let's say, these elements 2 3 5 7 4, right? And let's say you want to figure out in this input set whether there is a subset that, let's say, adds up to 11, right? So your W is equal to 11 in this case. So the question is basically assuming that you are given a black box. You are given a black box that can efficiently solve the subset sum W problem. So if you input a set S and ask whether there is a subset in the set S that adds to W, it will tell you yes or no. Okay, now using this algorithm, how can you construct an efficient solution for the two partition problem that we just now described? So recall once again that the two partition problem basically is, if you are given a set S, the question is whether this input set can be divided into two subsets S1 and S2 that add up to the same value, right? So essentially, if the original set had all the elements in the original set were adding up to some constant k, then the two subsets S1 and S2 should each add up to k by 2. Okay, so that's the two partition problem. So the solution to this problem is straightforward. If you are given the solution to subset sum W, note that if it is possible to partition S into subsets S1 and S2 such that they both add up to k by 2, right? Then essentially you have to ask this subset sum W whether in this set S there is any subset that adds to k by 2, right? Because if one subset adds to k by 2, the remaining elements would also add up to k by 2. Okay, so the question, the solution is very simple. You feed in the input set S and ask this algorithm whether there is any subset that adds up to summation of I equal to 1 to n half of this, right? So this is basically sum of all the elements in this set set S. So whether there is any subset inside this set S that adds up to half of the sum of all the elements in S. If the answer is yes, then it means the input set can be partitioned into two subsets satisfying this condition. Otherwise, no. So the solution is also summarized over here. So the two partition algorithm that we constructed using the subset sum W algorithm is efficient because of the following reasons, right? So let's think about what all our algorithm is doing. So the first thing it will have to do is it will have to come up with the sum of all the elements in the input set, right? So let's say it has to do S1 plus S2 plus Sn. Let's say this is C, right? So this operation is O of n. Next it has to figure out half of this value, so it has to compute C by 2. So doing this is, again, this is a constant time operation. Once you have this value C by 2, we are feeding in the input set S and this value C by 2 as input to the subset sum W problem, right? And we are calling this subset sum W only once. So therefore, if the subset sum W was running efficiently, then our two partition algorithm should also run efficiently. Now in this question we have to do the other way around reduction, right? So we are given an efficient algorithm for solving the two partition problem, and now we have to construct a solution for the subset sum W problem. So first of all, let's say your input set is S1, S2, so on up to Sn, right? And let's say that this S1 plus S2 plus so on, if you add all the numbers you get some constant C, right? And let's say in your subset sum W, the value of W is actually equal to C by 2, right? So if the value is C by 2, solving this instance of subset sum W problem using the two partition problem is straightforward, right? So basically if you have this black box that can solve the two partition problem, what you will do, you will simply feed in this set S and ask whether a two partition of this set is possible or not. Now if the question says yes, if this algorithm says yes, it means it is possible to partition S into two subsets S1 and S2 such that the elements in S1 all of these elements in S1 they add up to C by 2, and similarly all the elements here in S2 also add up to C by 2, right? So this is a straightforward problem to solve. So in this case, if the two partition algorithm said yes, the answer to your subset sum W is yes. If it says no, then the answer to your subset sum W is also no. However, what if your W is not equal to C by 2, right? You're looking for some other value of W in your subset sum W. Then how do we use this two partition algorithm? So we know that if W is equal to C by 2, or in other words, if C is equal to 2 times W, right, then the problem is trivial to solve. So here is what we'll do. We'll first find C, right? So we'll first add all the elements of the set of the input set and find C. Now assuming that this C is not equal to 2 times W, so W is the value that the subset sum is looking for, subset sum W. Okay, so next we'll find a constant K such that C plus K is equal to 2 times W. Okay, now we will transform the input set S. So our input set S was basically these elements S1, S2, so on up to Sn. We will now add this value K we just computed here, right? This K we will add to the set, and the new set is, let's say, S prime. Okay, so notice that this K is simply basically 2W minus C. So we have added that constant K over here. Now we will feed this S prime into the two partition algorithm and ask. So we'll feed this S prime here. So let's do this here. Let's say this is our two partition algorithm. We'll feed this S prime and we'll ask whether it is possible to partition this S prime into two subsets S1 and S2 that add up to same value, right? If this algorithm says yes, then it means in the input subset it is possible to basically break down this S prime into two parts such that they both add up to W, right? So why is that? Because notice that we just now added this constant K to the original set, right? And this K is computed such that S1 plus S2 plus 1 up to Sn plus this K is equal to 2 times W. So therefore, if it is possible to break down this S prime into two subsets, let's say SA and SB, such that they both add up to equal sums, then basically they both should add up to weight W. Okay, so now let's say SA and SB are the two subsets into which this can be broken down. So SA will have elements, let's say S1, S2, so on up to, let's say, some SI, right? And SB will have elements, let's say S of I plus 1 and so on up to Sn, right? I'm making this up, right? I mean, they don't have to be in this order, but let's say this is the division. Now notice that only one of these two subsets will have this constant K. So let's say SB has this constant K, right? So with this constant K, SB adds up to W. The other subset, however, this adds up to W even with just original elements. There is no added value over here. Therefore, all of these elements in SA were part already of the original input S. So if this two partition algorithm answers yes for this S prime, it means the original set had a subset that added to W. However, if this says no, then it simply means that there is no subset in the original set that adds up to value W. Okay, so this is how we can reduce the subset sum. We can solve the subset sum W problem using the two partition algorithm. The solution is also summarized over here, and also the part of the solution is over here. We now need to show that our subset sum W algorithm that we constructed is an efficient algorithm. So notice that our subset sum W algorithm, it first needs to add all the elements of the input set S to compute the value of C, right? So this is going to take O of n time. After this, it has to compute the integer k such that C plus k is equal to 2W, right? Now this is, once you have the value of C and you know the value of W, this is a constant time operation. And finally, our subset sum W algorithm calls two partition algorithm exactly once, right? And therefore, if our two partition algorithm runs in polynomial time, let's say O of n to the power C, then our subset sum W should also run in polynomial time. So the next question is about the graph construction that we did for solving the SAT problem using a solution for max clique problem, right? So recall that in the class when we had to prove that max clique is NP complete, we assume that, let's say we have a solution for max clique, then we using that solution we can solve the SAT problem, right? Now as part of the proof, recall that the SAT problem requires to figure out whether a given Boolean formula in conjunctive normal form is satisfiable or not, right? So the input to the SAT problem is a Boolean formula, but the input to the max clique problem is basically a graph. So as part of the construction of the proof, we had to transform the given Boolean formula into a graph, right? So what this question is asking us is, if assuming that you are given this Boolean formula here, you have to construct a graph corresponding to this formula to be fed into the max clique routine for solving the problem, right? And then from that graph we have to figure out whether or not the given formula is satisfiable. So let's solve this problem over here. Notice that this particular formula has three clauses. So let's assume this is clause 1, this is clause 2, and this is clause 3, and these are the literals in the clauses, right? X, Y, and Z. Here not X, Y, Z. This is X, not Y, not Z. So in this case, so recall that the vertices of the graph that we want to construct are the clause comma literal in the clause. So clause comma literal pair. So basically we'll have three vertices corresponding to C1, three vertices corresponding to C2, and three corresponding to C3. So here this picture over here shows the vertices. So notice that here we have a vertex. These are the three vertices corresponding to clause C1, these are the three vertices corresponding to C2, and these are the three vertices corresponding to C3. Let's now draw the edges. So recall that there no edges are allowed between vertices of the same clause, right? And the other constraint was you cannot connect two vertices if they have literals complement of each other, right? So for example, we cannot make this connection. This is not allowed because here we have X and here we have not X. So both X and not X cannot be set to true simultaneously, right? That's why this edge is not allowed. So the idea is, whatever edges you are connecting, they should represent compatible vertices. So the literals at the vertices that are connected through an edge should be able to set to true simultaneously. So that's the idea. So let's now draw these edges. All right, so let's now draw all the edges from this node C1Z, right? So notice that Z is compatible to not X, so we can connect these two. Z is compatible to Y, so we can connect these two. Z is compatible to Z itself, so we can connect these two. Z is compatible to X, so we can connect this. Z is compatible to not Y, so this can be connected, but Z is not compatible to not Z, and therefore these two cannot be connected, right? So likewise we have to draw all these edges, finish the connections and finish the graph. Now in this graph, if we can find a clique of size slice k equal to 3, right? Because there are three clauses, so if we can find a clique that has three vertices, then the formula should be satisfiable, right? So let's see whether we have a clique of size k equal to 3 here, right? So if you notice, so there are actually many cliques of size 3 here. If you complete the graph there, I haven't completed the graph yet, but if you keep drawing, so here you see these edges, right? So this and this, right? These three edges, so these three vertices, they form a clique, right? So this is a clique of size 3 because there are three vertices. So if you simply set the letters here, here, and here to true, then your formula should be satisfiable, right? So what this is saying is basically if you set y to true, and this is also y, so these both are y themselves, and then this x to true, then the entire boolean formula should be satisfiable. Let's see whether that is true, right? So basically if you set this y to true, this y would also be true, and x also is true, right? So this x will become true. So notice that this is in conjunctive normal form. So if this y is true, this particular clause becomes true. If this y is true, this clause becomes true, and when x is true, this clause becomes true, right? If all the clauses are true, the result of this boolean formula would be true, right? So this is one possible satisfying example over here. The solution is all the construction and the solution is summarized over here. Another satisfying assignment is provided here on this slide. The next question over here is about parallel algorithms. So we are given this code over here for multiplying two square matrices, and this is multi-threaded code. As you can see, there are these parallel keywords, and the question is asking us to compute the work, the span, and the parallelism or the max speed for this code, right? So recall that work is basically the time it takes to execute a program on a single processor machine, right? So if you execute, so basically what happens if you execute this process on a uniprocessor machine sequentially, right? So notice that we have these three nested for loops here, right? And each of them is going from 1 to n, right? So basically the work the work which is simply given by t1 of n is in this case big O of n cube because of this nesting over here. So that is straightforward. Now the next question is, what is the span of this algorithm? So the span is basically the time it takes to execute the algorithm on infinite number of CPUs, right? So if you had all the parallelism that you would ever need, how much time would that take to execute this code? So let's think about this. So this program over here, let's say this starts on a single CPU, right? Now the first two lines of code, like this line and this line, these are sequential, so these would be executed on the single CPU. But when you reach this third line, because of the parallel keyword, assuming you have infinite CPUs, the compiler would want to replicate or copy this program, this process onto multiple CPUs, so that each iteration of this for loop can execute on a separate CPU, right? So we have seen that this replication takes some time. Let's say the compiler is using a divide and conquer approach. So in the first step it branches off to 2 CPUs, then you branch off to 4 CPUs and so forth, right? So how many steps would it be before you reach on up to n CPUs, right? So to reach up to n CPUs, if you're following this divide and conquer approach, this is going to be log n, right? The height of this tree is going to be log n. Now when you reach here, you are done replicating the for loop in line 3, but now you have reached this next parallel for loop in line 4, right? So this is also going from 1 to n. So the compiler would again want to replicate each of these nodes, which represents this parallel for loop, onto n more CPUs, so that each of these iterations of this inner for loop can also run on independent CPUs in parallel, right? So basically the same thing would start here. Let's say you start replicating this inner for loop here, you using the divide and conquer approach. So again, before each of this for loop has a CPU of its own, right, all the way up to n, this subtree from started here, this is going to be again, so this from here to here, this is again going to be a log n height, right? And then once you reach here, these leaf nodes would be responsible for executing this sequential for loop, the third nested for loop, right? So each of these nodes is going to do big O of n work, right? Because this k is going from 1 to n. So what was the time complexity of doing this? So essentially this t infinity n, this basically comes to, you have to first replicate this log n step, so there is O of log n, then you have to again do this log n replication, so this is again big O of log n, and then when you reach these leaf nodes, you have to do big O of n work, right? So this is big O of n. So this expression over here is essentially big O of n, right? So because the big O of n dominates all of these log n. So this is our span. Okay, so the span for this algorithm is t infinity n, which is basically big O of n. Okay, now recall the max speed up or the parallelism is basically given by the work divided by the span. So in this case, that would be your work is big O of n cube divided by span, which is big O of n, which is simply big O of n square. Okay, so this is our solution for the problem. So the answer and this is also summarized over here, and here is the final answer, big O of n square. So here is the next problem about parallel algorithms. We are basically given a parallel algorithm for merge sort. The only parallelism in this code is basically coming from this spawn keyword in front of a call to the recursive call to merge sort on the left half of the input array. This merge function, this is still sequential, right? There's nothing different about this code. The only parallelism is from this spawn keyword and this sync keyword. That's it. So this question is asking us to compute the work, span, and the parallelism for this code. All right, so the work, once again recall, is the time it takes to execute the code on a single processor. So forget about this spawn. Let's say there was only unicore uniprocessor machine, so this code was executing sequentially on it, right? So if that was the case, how much time would it take? So recall that the recurrence for merge sort was 2 times t1 n by 2 plus big O of n, right? So why is that? So basically you had this array, this input array, you break it down into two. So if your input array was size n, you break it down into two halves of each of n by 2, right? And you recursively sort these two halves, merge sort, and then you merge these two into one sorted array, right? So basically, if it took time t of n to solve this to sort the original array, then sorting each of these halves would take t of n by 2 time, right? And then merging was O of n step. So that's why we get this recurrence over here, and from master method it is clear that this is big O of n log n, right? So also recall that the complexity of merge sort was n log n. This is basically your b, this is your a, right? So n to the power log 2 base b of a is simply n to the power 0, I'm sorry, n to the power 1. So so f of n is the same as n to the power log 2 base b of a, and therefore this is case 2 n log n. Okay, so the work done is order of n log n. Let's now figure out the span of this algorithm. So recall that span is basically the time it takes to execute a process on infinite processors, right? So in this case, in your merge sort, if you have, let's say this is your input array of size n, and you're breaking it down into two halves, n by 2 and n by 2, and now let's say this, the original one took time t of n, and now you have infinite processors, so you can execute this half in parallel to this other half, right? So both of these are happening in parallel, and then finally you will have to do this merging, which is going to take order of n time again, right? So because these two halves are happening in parallel, the total time it takes, this t infinity of n, is going to be max of t infinity n by 2 comma t infinity n by 2, right? This is not going to add up, and plus you have to do this finally this merging step, which is order n, right? So max of t of t infinity n by 2 and n by 2, these are the same terms, so it's simply t infinity n by 2 plus O of n, right? So this is your recurrence. So recall that this recurrence, this is basically the same as saying that t of n is equal to t of n by 2 plus O of n. From master method, you can see that this is simply big O of n. Okay, so basically what that means is the span for our algorithm t infinity, so let's get rid of this over here. So basically the span t infinity of n is simply big O of n. Okay, so from here we can compute the max speed up or the parallelism, which is basically the work divided by the span, which in this case would be work is O of n log n divided by O of n, right? So which is basically simply so this is basically O of log n. The solution is also summarized over here. So this basically brings us to an end of this review. I hope this was helpful. Please let me know if you have any questions. Good luck with your exams. Thank you.